So problem number 3 on exam number 2 has a ramp that you can use to launch a block, well, a spring that you can use to ramp a block up a ramp. You're not told the angle at which it's launched, but when it gets to the end of the ramp, it's traveling at some angle in a parabolic path. We'll focus on the peak of it for at least part of the problem, okay, which is a height h above the base of the launching system. And it comes down along this parabolic path and encounters a mirror image of this ramp, except there's friction, length L of track with friction that brings the block to a stop at the end. Okay. So the first question that you're asked is, how much work does the normal force do? And the answer is 0. Okay, and you've seen this same question in other exams, etc., and homework, and you should realize it's 0 because work is actually the vector force d dotted with the vector displacement d, but n is perpendicular to the path everywhere, to any little element of the path if you like. And so if the normal force is always perpendicular to the path, always pointing perpendicular to the direction in which the block is moving, then that tells you that the work is 0. Okay, so that's the explanation. And there was a requirement that you justify your answer, not just write it down. Part B asks, how fast is it traveling at the peak of the path? How fast it's moving here, and you're allowed to use all these parameters, but you don't have the angle theta. And so whenever you're asked a question like this, you should remember that the first thing to do is think of work energy. And in this case, we can say that there's no loss of energy for that part of the path from the beginning until the peak, as long as you use potential energy for gravity. So the final energy equals the initial energy plus any work that's done. No work is done between the launch and the peak of the path, except by gravity, which we'll take into account using the potential energy of gravity, where we'll define U equals 0 for gravity at the original height where it's launched. So now we can start writing out terms. What's E naught? Well, E naught is the initial energy whenever you compress the spring, prepare it for launch. You have to do work to do that, but that's not what we care about. So the spring will have an energy 1/2 k naught squared when you compress it, preparing for the launch, and there's no potential energy because you're at the original height. The final energy, in our case final, is the peak, because that's what the question asks you, what's happening at the peak. At the peak we'll have a kinetic energy, 1/2 mv peak squared, and now it's above U equals 0, so it also has some gravitational potential energy. That's plus mgh. So these two terms have to equal each other. E final equals E naught, or this has to equal to 1/2 kx squared. So all you have to do is solve this equation for Vp. Velocity at the peak will just be, well, take mgh to the other side. We'll have 1/2 kx squared minus mgh. Sorry if I switch back and forth between small and capital. Okay. I have to multiply both sides by the 2 over m to move this term to the other side. Okay, so I'll have 2 over m, and I have Vp squared, so I'll have to take the square root. Okay, and that's it. You can simplify it if you want. You can also write this as kx squared. Let me just do it. It's also equal to kx squared. This 2 cancels that, 2 over m, and this m cancels this m, so minus 2gh. So either of these forms is fine for the answer. Okay. Part C says, what's the minimum length of friction track you need here at the end in order to bring it to a stop? I purposely don't allow you to use h. It's not that you can't. You could say, well, it's at the peak h, it's moving with a certain velocity. Let's go and solve for how much work friction has to do to stop it. But I wanted to force you to skip this part of the analysis for part C and just look at initial and final, because that's all you need. Okay, but in this case, we'll have the final energy at the end of the track when it's stopped equals the initial energy when it's compressed by the spring plus work, and now there is work done. It's going to be the work done by friction. So E naught is still 1/2 kx squared. E final equals 0 because it's the stop at its original height. Okay, but there's work done, and that'll be negative work done by friction because friction will oppose the motion. Negative F sub L, which is negative mu. It's kinetic because the block's sliding along the plane. And the force of friction is mu k times the normal force, so it's NL. And this will be equal to negative mu k, and hopefully I don't have to write out the coordinate systems and everything. You'll know that for this situation, n equals mg, so negative m mu k, mu kinetic, mgl. And I'll put it all together. E final equals E naught plus the work done. And so what I've got is 0, because that's E final, equals the initial 1/2 kx squared plus the work done, and the work done is actually a minus mu k mgl. Okay, and just solve for L. That's what you're asked for. In this case, L is going to be equal to kx squared over 2, 1/2 kx squared, divided by mu k mg. Done. And that's it.